Now we look at the idea of chemical equations. Now we've covered briefly how the fact that the chemical equations need to be governed by the law of conservation of mass. Now that's the main part that you covered in first year chemistry. If you have 5 oxygens on this side, you have to have 5 oxygens on this side, and so on and so on and so on. The law of conservation of number also applies. So it can't just be mass. You can't say, well, I've got 5 oxygens here, but what I'm going to do is I'm actually going to turn that into, 90 hydrogens. Okay, that would technically satisfy the law of conservation of mass, but it wouldn't satisfy the law of conservation of number. We're not going to destroy atoms at this point. It should also uh, be governed by the law of conservation of charge also. We talked about this real briefly with redox, how if you have 2 electrons over here, you also have to have 2 electrons over here somewhere. You can't just make up electrons. In addition to that, we also talked about the law of conservation of energy and how that needs to be also accounted for. But these are concepts that we're going to cover later in the year. Really, we're focused on these two at this point. So we start off with the idea of balancing an equation. It says the first thing you need to do is you need to write an unbalanced equation. So you need to write the actual equation that predicts the product. And we'll talk about predicting products later. But you predict the product. Okay, once you've determined how many atoms there are on each type, you kind of set it up as a left side and a right side. And then you look for, okay, what can I do to multiply these values out so that I have the same number on both sides? You have to multiply them by a whole number. And really, you can write out this in-depth procedure, but really it takes getting used to. You've got to practice the idea of balancing chemical equation. It gets to be pretty much second nature. Now, one thing that we didn't really do in first year chemistry is you're supposed to state put the state of matter there. So you're supposed to say not just X, but you're supposed to indicate that X is a solid. Okay, that's what that little S stands for. You're supposed to indicate that H2O is in its liquid phase. That's what the L stands for. Okay, you're supposed to indicate that hydrogen is in its gaseous phase. So it's really important that you be able to specify what state they are in, because if you were to put it in these phases, there's no reaction. So this won't happen because water's in its solid form, which we know is ice. So some reactions will occur, some reactions won't occur, even if they're the exact same thing. So it's really important that you specify the state of matter. Now this one right here, this AQ, is indicating an aqueous solution. What that generally means is it means some sort of solid has been dissolved in a solution. Usually it's a salt or something like that. Sometimes it ionizes, sometimes it doesn't. But you need to be aware of the idea that an aqueous solution is one that allows them to mix very thoroughly in some sort of solution. We look at an example. It says balance the chemical equation below, and then it says discuss the role of copper in the reaction. It says determine whether the reaction can be completed without using copper using an alternative method. Okay, and if you were to look here, you have the idea that you have 6 carbons here, and you have 6 carbons here. So because I have my carbons match up to begin with, I'm going to go ahead and start with the idea that I have a 1 here. And if I have a 1 there, then I generally have to have a 1 here, because I have to have my carbons match up, and there is no other place for carbons to come from. Now, if I have 6 here, I've got 6 hydrogens, that means I'm going to have a 6 here. Okay, if I have 6 hydrogens, that balances my hydrogens out, but now I get to take a look at the fluorines. As written on the right side of the equation, I have 6 fluorines from here and 12 fluorines from here, which is a grand total of 18 fluorines. If you were to look over here, I've got F2, which means that for everything that I add, there's going to be 2 fluorines. So what I can do is I can actually put a 9 there. When I put a 9 there, 9 times 2 is 18. That's going to balance out. Now, if you look in terms of copper, I can just put a 1 and a 1 there. Now, if you notice the role of copper doesn't actually change anything in the reaction. Copper's there and copper's there, but copper doesn't take place as the chemical reaction. It doesn't take a hydrogen or a fluorine or anything like that. So instead, a lot of times you'll refer to copper as a spectator, but generally what it's doing is it's acting as a catalyst. A catalyst is generally something that makes the reaction go faster, and a lot of times instead of seeing it on in the chemical equation itself, a lot of times you'll see it written above, like it'll say solid copper above the arrow, indicating that it's something to help the reaction, but it's acting as a catalyst.